Alright, hell yeah. So today we're going to go over one of the hardest things in material mechanics, and that's the strain transformation equations. Now these are probably harder to fathom than the stress transformation equations, just because the geometry seems a little bit odd. So we got material mechanics with Gear, and then we also have another book, Material Mechanics, and this is Hibbeler. So I definitely, I just have these two books in my wheelhouse, and having both of them, if you ever get confused in one book, maybe the other book explains it in a little bit different way. So hell yeah, and that's what we have going on. So in the Gear book, we have a little element, and we know that we have some change in length in the x direction, we have some change in length in the y direction, and then we have some sort of rotation of the element. That's going to be what strain is. Strain is a deformation. It's going to be a stretching, two different directions. It can also be a shrinking, So stretching is just the positive change in length, where shrinking is just a negative stretch. And then we have to have some sort of way to show like shear. So shear is just a rotation. Basically, if I have a square box, like these lengths don't change, and so we'll have like a rotation like that. But to, if I have a parallelogram that rotates like this, well, it looks like that length changed. So what happens is that we have something like this. So we have, if we're going to rotate, let's say we rotate in the positive direction. So this was going to go this way, and then we're going to rotate in. And then if we do that, then we all sides are the same. And so we're going to talk about that, just because if you do have a rotation where all these lengths stay the same, then you get a little bit of change in angle here, but then I had to move this up, so you get a little change in angle there. And so what we have for this is like, hey, we're just going to fix one of those, and then we're just going to do that. So yeah, we're going to get that angle, and that angle is going to, it would cause this element to rotate. Now the whole idea of the transformation equations is just like, well, let's rotate our element and then see what the change in length this way is compared to the change in length that way, and then we're going to see if it also rotates. Cool. And then so the bummer is that they just show that as a diagonal line, and it doesn't, I don't think it shows you the full picture when all you do is like, hey, if the diagonal line changes in length, that's going to be the change in length of the the element. And maybe that's okay. I mean, if we have a diagonal line, hey, that's going to change in length, so that's going to be the change in length in this new direction. But if we wanted to find this change in length, well, we just say, hey, we're just going to find the equation for this change in length as a function of theta, and then we're just going to rotate it another 90. So I just don't think that also does it justice either. I don't think trigonometry is something we all have a grasp on mentally with the symbols. I think we need to see it to believe it, and so that's what we're going to do. And then hell yeah. So both Gear and Hibbeler use diagonals for their proofs. You know what I mean? And so I go a step farther. Well, and what both of these do is that they say this diagonal is a new length. You know what I mean? So if I have an element down here of dx and dy, they're showing this diagonal as the hypotenuse. You mean, so that's a bigger diagonal. And so this is the first thing that this is a small element of a bigger, bigger beam or something. So this is it's an infinitesimal element. You can make it as big as you want to have like a actual, perspective of it. In some cases, you might be able to make it as long as you don't have shear. Because the first problem is just like, hey, an 8-inch by 4-inch chunk of metal is going to be stressed, and that stress is going to be pulled this way and then crunched this way. Well, cool. That stress is going to cause a strain, a change in length. And so that whole thing changes in length this way, and the whole thing changes in length that way. So from that perspective, you can look at the whole thing as a, you don't have to make it an infinitesimal, because every little part of that is changing this way and changing that way. And so hell yeah. But the second they want, like, you know what I mean, hey, what does the diagonal do? Then well, I guess I don't know where I'm going with that. But just in this derivation, they, like, just think about this. If this is your element that you're using, and you know it's changing like this way and changing like that way, just focus on these two. Hey, you know what I mean? That sounds just fine, and I got a mental grasp on that. But then when we have a rotated element, hey, we're going to actually take this blue thing and then rotate it. And then so this blue thing is now going to be right here. And then guess what? It has dimensions dx and dy. And when we rotate it, it still should have dimensions dx and dy. But when they say, hey, this diagonal is ds, that ds is much bigger than dx. And I think that's probably the first place that people might. That's where I got in trouble. I was just like, hey, this makes no sense. So hell yeah. So without further ado, we're going to walk through the way that I do it. And then I think before we do that, this book was probably better in showing that we have an angle difference here, where this book does not show that angle difference. But because of that, this derivation made it way easier to see the change in length. So if we are talking about this diagonal, and hey, like this thing moves this way, so that's this picture. Well, cool. Now, well, I don't even like the way they do this either. Yeah, it's fascinating. You know what I mean? Like the trigonometry might be right, but it's just like there are certain things about this book, about both of these proofs, that are just like, I don't know. You know what I mean? So we're going to do it the way that I have been practicing at the coffee shop. And hell yeah. You know what I mean? We got a lot of practice. We kind of sat down and we tried to crush out, you know what I mean? So here's kind of the effort. You know what I mean? Just doing it and then redoing it, getting the equations from different perspectives. You know what I mean? And so that's what we're going to do. And so in this video, I think I got it boiled down so we can do it one shot, and we can get any equations you want. And I think it can explain the strain. And I don't mind making, you know what I mean? This has been a 10-minute intro, and that's fine. So hell yeah. So sit back, relax, and here is the strain transformation equations. Alright, hell yeah. Okay, so we're going to do it. You know what I mean? And I think this is the way that you should do it too. I mean, I've been doing this for quite a bit. I'm sure I'll come up with a better method. But we're going to make our XY axes. I'm going to do it out here because when we rotate stuff, it's going to be over there. So that's kind of the first thing. And we don't have to get too technical, but I do enjoy the way they do the proofs is to have an element that's kind of longer than it is taller, especially when we're dealing with angles. Because for two reasons. Now we can see that, hey, this angle of rotation is theta, and this angle is smaller than this. So that's kind of the first thing. If I see that this is theta, I'm going to say this is phi. And then so anytime I have a 90 degree, if I can identify one of these, I know the other. So if I know this is 90 and this is phi, this has to be theta. Alright, sweet. So same thing here. I have a 90 degree triangle. If this is phi, this has to be theta. If this is theta, we have a 90-degree triangle. This has to be phi. Now, we're going to get to the point where our little triangles get small, so I am going to use this method. So if I have, like, hey, this going on, where I just have kind of small little triangles, and I don't know what, hey, this is, so I'm just going to say the line is theta, and then I'm going to say this dot is the opposite. So that way, even if these triangles get real small, I can keep track of things. So if I do this, I'm going to say, hey, this is a tangent, so this is 90. And so how would I do this? Because the other thing that we have for trigonometry is if I have this going on. If this is 90 and this is 180, and I know this is theta, and I'll just write it in here, this is theta, then this angle is phi. And so that's another one that if these get real small, I can say, hey, this is 90, and then I can say that is, if I do this, that's going to be synonymous with theta. If I do a dot, that's going to be synonymous with phi. And I think this is very good because we're going to have this happen so much. And even, and then the other trick is this angle is from the horizontal. And so there's two aspects of this. One, theta is from the horizontal, and it's a positive slope. The slope is positive. Cool. So that means that a perpendicular line, the slope is going to be negative, and the angle from the vertical is going to be theta. So here is theta, and here is theta. So if I have, so now I'm just going to keep that in mind. So I know that this is my rotated angle from the horizontal. So if I come to the horizontal, but I want the angle to go this way, well, I know that this is going to be a positive slope, and then this is theta. Just as I know that, hey, this is a positive slope, and this is theta. And you kind of have this little, I call it the bow tie method. Same thing as if I have a vertical. The slope has to be negative, so if I start from this point, I either have to go this way, or I have to go this way, and then this will be theta. Cool. And again, I can, from the vertical, we're going to do a negative slope. This is theta. I'm just going to use that for my nomenclature. And then so here's a 90, and I'm going to say these are the complementary angles. Cool. Alright, so just as the proof does, we still want this element to be an infinitesimal element. But, so mentally it has length. It doesn't have zero length. But we're going to say this is dx, and then this is dy. Cool, so that is this rectangle. And this is going to be the x-axis, and this is going to be the y-axis. So what we want to do is we want to rotate this up to this x prime axis. I'm going to use x prime, probably, just because if you throw a subscript, I think sometimes it's harder to do it. When you're writing, it's harder to do this subscript and keep it in that right location, where x2 might look like that. So hell yeah, so x1 is going to be x prime. So a lot of books will call this x1. We're just going to call it x prime. And then so perpendicular to that, we have y prime. And again, hell yeah, the slope is positive, so we had a perpendicular. That means that this is theta, because we have that negative and from the horizontal. And it's going to be perpendicular with this. So hell yeah, so this is theta right here, and I'll throw that in there. Okay, so if we rotated this element just right up to here, we kind of have this going on. This shortens, and then we have this rectangle. All right, booyah. And then what happened with this? So this whole chapter is plane strain. So we only have 3 things that are going on, and they're going on in this sheet of paper. Like this is a cube, like it goes into the, you have a little cube, And the three things that can happen is this cube can lengthen this way or shorten. That's one. It can get taller and squatter. That's two. And then it can make that diamond shape about the XY plane. And so, and then from, and this is like the first like asterisk is like, hey, well, didn't we learn that if forces are pulling on something and it lengthens this direction, like doesn't Poisson's ratio make it squeeze in the other two directions? And yes, that's true. So that's why these problems are very specific of like, hey, let's shorten something, but then let's bound it between two metal blocks. You know what I mean? So rubber, so some of the problems are like a rubber block is being squeezed, and in this direction it's being sandwiched. So it can't bulge out in the Z direction. And so that's a very important aspect of plane strain. Cool. So from that, you know what I mean, you probably want the next phase. So what, and then what this gives you, the whole goal is to be like, if we can find, if we can rotate at a certain angle, we can figure out, you know what I mean, what the change, like, how much is it going to change this way? How much is it going to change this way? And then if we do have this rotated element, how much is it going to skew, you know what I mean, and shear? And then we can, and then because it's a circle, we can just rotate it up to here. We could rotate it farther, and then we can keep doing that. So we could have like 360 equations and 360 different values, you know what I mean? And then we would want to, you know, plot those. And so, and what we'd be getting is the lengthening, you know what I mean, the lengthening in this direction. But check this out. So like the first aspect that's a little bit heady is like, hey, if I rotate this up to here, I still want to know how much it lengthens this way, and then how much it lengthens this way. But okay, so that's the first thing that's a little tricky, is like we only need one equation. Because if I rotate this thing all the way to here, and then so let's do that. So this will be the base, and this will be the height. Cool. So now this is dy, like this length is dx, obviously. And then what we want to know is how much it's going to lengthen this way. And so the equation, when we rotate this up to here, like the equation that we'll get to lengthen it this way will be in terms of theta. Well, so will, if we rotate this all the way over to here, the equations that we're going to lengthen it this way, which over here, this now is x prime, and this is y prime. And let's do x double prime and x double prime, just so we don't, we have a little bit of a different notation. But yes, the equation of lengthening in this direction is just where theta is just this bigger value, which is just theta plus 90. And so, therefore, if we get an equation for the lengthening, and see how, like, the textbooks, they'll just say, hey, the lengthening of this diagonal, and then worse, they call this diagonal this line, where if we rotated this up, this diagonal, we can, so what I'm going to do is just say this diagonal is dx. You know what I mean? Because it looks like we have an element, we visibly rotated it, and then I want to know how much it changes in length in this direction. I really don't care how much it changes in length in that direction. And that's the other thing that I don't know if I have to get better about, but when we talk about strain, I always just like to think of it as stretch or a change in length. But it's a change in length per unit length, and so that's the technical value of how to say it. And so so if I know that this thing has a strain in the x direction, this is the epsilon, this is the symbol for change in length per unit length in the x direction. Alright, hell yeah. So we're back, and So yeah, so I think where I'm going with this is strain is going to be a change in length per unit length. So, you know what I mean? In this direction, we have a unit length of dx. You know what I mean? So, and let's just write the definition of strain. Strain is going to be a change in length divided by initial length. So you can call it L naught. You could be like change in length divided by length initial. And then you could say change in length is length final minus length initial divided by length initial. So I think it's good to write the strain equation in as many ways as possible, because it's actually a very simple equation, but it's useful. And we got an equation of three things. And so the first thing we want to do with an equation of three things, especially if you're going to get into electrical stuff, is it IRV? Or is it I is equal to V? I have no idea. You know what I mean? But let's say it is this. Hopefully I just ruined it. You know what I mean? But I would say that V is equal to IR. And then we would have... and then, see, I don't think this is right. But maybe it is. Cool. And then let's solve for I. I is equal to V divided by R. And let's solve for R. R is equal to, get the I downstairs, V divided by I. So there you go. So we have three equations based on one equation, and sorry if I just totally ruined that. But here's the strain equation, and so we could say that 1, strain is change in length divided by initial length. We could say, we could get this upstairs and then get this downstairs. So the initial length is change in length divided by strain. Cool. And then we have change in length. And this is kind of the one that we're going to be using quite a bit. Change in length, get this upstairs, is strain times initial length. Cool. So if I know that this length strains, and you know, that's the value they're going to be giving you, I know that's going to be a stretch in this direction. But then if I take my, whatever I'm working with, and I'm just going to say, hey, here's a little chunk of material, I want to know how much this chunk lengthens in this direction. And so I use this equation. That change in length is going to be the strain in that direction times the initial length. So we have strain EX times DX. Hell yeah. So this is the first thing that we're going to run into, is that when we rotate our element up here, I think it is useful to keep this length as DX. But we were not given what the strain in this direction is. You know what I mean? We were just given it in this direction and this direction. And so so this is the next thing we're going to do, is we're going to drop this down and then drop this over. And so, you know, this is still useful because we're still saying we had this original dx dy element. We rotated it up. Sweet. So now we still have this dx dy. And what we're interested in is how long this one changes in length. You know, what's the change in length? And we're really interested in the strain in this new direction. And back to our equation, it's going to be the change in length in the x1 direction divided by the initial length in the x1 direction. So the initial length is just dx, and the change in length is what we're going to be, you know, like solving for. But check this out. You know what I mean? If I say that this length is dx, and when we increase it, we're going to be, like, everything's going to be a function of, so this upstairs, and the textbooks don't do this. They use this diagonal length, and they're going to say that's dx prime. And that's fine. That's still associated with a bigger chunk in this direction. You know what I mean? But if that's dx prime, like, you're probably going to have a dy prime, and then you're like, well, what's the dy distance? And that can be confusing, where even just like right here, we're just solid, because we've taken the same dx dy and rotated it, where this is still dx, this is dy, and then all we have to do is just kind of drop down and then make a smaller chunk of material. And the cool thing about strain is it doesn't matter. Like if I say I have a strain of a certain quantity, and this is the length of the material, and it lengthens this much. Or yeah, we'll say this is the length of the material, and it lengthens this much. Okay, no, sorry, we're going to have to go the other way. If this is the length of the material, and it lengthens an inch, okay, let's say I just want to half that material, you know what I mean, and then kind of inspect half of that length and see how much that's going to lengthen. Well, it's going to lengthen half of an inch. And so so that's what we're getting at. And, you know what I mean, this is still a small chunk out of a big, you know, like metal project or you know, bridge or whatever, beam. And it's infinitesimal. It's literally like what's happening at a very small microscopic point. But still, since everything lengthens, you know, if I have 1 meter of steel and it lengthens 2 millimeters, I could have 1 millimeter of steel, and it would lengthen 1/1000th of 2 millimeters. You know what I mean? So that's you know, proportionally how much it would lengthen. Cool. So I think this is still pretty decent visually, where we have rotated up our element up here, but we still need to know what's going on just in this direction. And so I'm going to basically have this square, which has a hypotenuse of dx. So then I know this length right here is dx cosine theta, and I know this length right here is dy is dx, the hypotenuse, times sine theta. You know what I mean? And sines and cosines are just percentages of the hypotenuse. And then, so if I want to get the change right here now of this smaller rectangle based on the strain that's given, this change from here to here, we are going to call, well, and then what's that change in length? So change in length is the strain times the initial length. This is the initial length. And then the strain is still the same in the x direction. Even though we've rotated it, what we've done is just kind of, we've rotated it, so we're interested in the change in length of this. What we're going to do is we're going to take this smaller rectangle, and we're going to say, hey, this lengthens. And we're still going to take this rectangle, and we're going to say, hey, it lengthens in the y direction too. And we're also going to say that we are given an initial, so plane strain says you're given an initial strain in the x, strain in the y, and then a rotation, an angle rotation about the xy axes. Cool. And then so kind of jumping ahead is if we have a change in length in this direction, this point is now going to move over here. And then so this line for sure changed length. This line is now over here, and it seems to be much longer. So now we're going to use trigonometry to find how much longer. You know what I mean? And so, and we'll talk about that in a second. Now that's due to the strain in the x direction. We also know that there's strain in the y. So we're going to take this point and strain it in the y. This rectangle is going to get bigger this way. And check it out. This point is now up here. And then so it looks like this got longer. Cool. So keep that in mind. So we're going to get an equation based on how much this length was, and then still these angles. And cool. And then a little foreshadow. We're going to treat this as a hypotenuse. And we're going to make a little right triangle, kind of drop down right triangle, and we're going to have two components, one in this direction, and then one in this direction. The cool thing about solving the transformation equations is both of these are going to be useful. For now, we just want the change in length in this direction, so that's going to be this component right here. Over here, we found that this rectangle lengthened this way, and so it lengthened this way this much. I'm going to treat this as a hypotenuse. And then have and then have these coordinates x1, y1. And so this hypotenuse has two components, and it's this component that's going to be the change in length of this diagonal in this direction. So just like the textbooks, we're looking at a change in length of a diagonal. It looks like this diagonal was associated with that original, that original rectangle, and it can be. It can be. I just think it makes the math just a little bit harder. Where if you say, hey, again, if we rotate this up to here, cool. So now this hypotenuse is still dx. That makes the most sense. But it requires us to kind of drop down and have a smaller rectangle. But due to strain being the same, strain is proportional change in length per, so this is a shorter length, so this length is a little shorter. But still, what comes out in the wash is we're interested in this change in length, and that's what we're finding. But the strain in this direction is that change in length divided by the original length. And so our change in length is going to be smaller, but our original length is smaller. And it still keeps with the idea that we had a rectangle of dx dy to begin with. So I just think that's my main motivation for making this video is like, hey, if we're going to rotate this element, don't change its length. Don't rotate it and then change its length and then assess it. Just keep it the same. And I think mentally, and you're going to see that the math just really works out where you don't have to do any trickiness. All right, hell yeah. And then I think the hardest one to do is like we're also given an initial shear strain. That's going to be, this thing is going to do this at a change in angle. And even right now, I think classically, you're going to have a shape like this, and it's going to turn into, and how to draw this is like, positive shear strain means that, hey, we probably have a force this direction, and a force this direction, and we have opposing forces. So if I find a force that's causing a shear, I'm going to have an equal and opposite on the other side. And then that's going to cause this to rotate this way. And then I need equal forces to rotate it that way. So that's the way. And these could be synonymous with the shear forces, or they could also be the shear strains, tau. And what happens, the easiest way to look at this is to fix this location. And this line is going to go up to here. And then so it's going to leave here, go up to there, and this point's going to go. None of these lengths are going to change. And then so this is also going to make this line go this way. Cool. These 2 points have to be in the same location, so we're just going to square them in, and that's going to be right here. So now this length to there, and this length to there, and this length to there. See, and this is wild. Because I just said that these lengths didn't change, but no, they didn't. Yeah, you can draw this without those lengths changing, just fine. Okay, sweet. And so that is going to be what happens with shear, and you're going to get a small little angle to form there, and a small little angle to form there. And all right, hell yeah, we're back. And so what we're going to quantify as shear is this angle reduction. This used to be a 90, and now it's not. It's a much smaller angle. So this angle theta was 90, and now this angle theta is less than 90. And we probably should have used some different angle. You know what I mean? But anyway, and then so these two angles combined to give us the shear strain. So this is an angle. It's going to be in radians. And it's going to be the combination of both of these angles. So all they do, technically, in the textbooks is this probably isn't even the case anyway, because we fix this point. And you know what I mean? If you have true shear, it's probably going to be rotating about a neutral axis. But we still have to quantify this angle reduction, and so we're going to put these axes right here. So there's no difference in coming in and then putting this axis right here along this flat line. And if we do that, then this angle becomes the same thing as both of these angles combined. And so that's typically how you're going to see this. And yeah, and that's totally legit. Yeah, cool. Yep. So booyah. All right, nothing more on that. And then so how do we show that on our diagram? Is that we have this is the y-axis and this is the x-axis. So you got to be paying attention to this 90. And since we're saying that positive shear, we're gonna have this pivot point, kind of the center of the center of the axes. And in the positive x and the positive y direction, we're quantifying this to be 90. And if this angle reduces, that's going to be positive shear in the xy plane. That's going to cause a diamond shape to happen here. The other thing that can happen is negative shear, where you fix this point. And so how that would look is you'd have a downward force here, or a shear, and then that would accompany by an upward. That would cause rotation this way. To finish out the arrows, we need a rotation that way. This arrow and this arrow. So these could be representative as shear, or they could even be represented as forces acting over the area. And never forget, this is a cube, and we're just looking at this face. And these are happening, these forces or pressures are happening on these faces. And so if we have this, I'm going to fix this location. This line is going to go down, and then this line is going to go over. Because if I'm fixing this locations, you have to go to the extreme two ends to see what's going on. Now, if this line goes down and this line goes over, this point still has to be attached. And so these 2 points can't separate. So square it in and then just draw it right there. And now just dot your, connect the dots. This is, I should make a shorter video, but I do this a lot in all my videos. And so now we have the same diamond shape, but it's spilling into the second. If this is first quadrant, this is the third quadrant. It's spilling into the second and fourth quadrant. And this is associated with a negative change in angle. So this is negative shear, where this angle now got bigger. Now you might be like, well, shouldn't that be positive? Well, by sign convention, we're needing to say, and this goes back to what is sign convention on this. We're needing to say that in general, this is the x and y axes. This is our little cube. This is going to be the positive x face. And we have a negative, and then this is acting in the negative y direction. So this positive and negative make a negative shear, and a negative shear causes negative shear strain. And so that is the reason, you know what I mean? And so just know, that's why you have to think of positive shear as it making a diamond shape in this direction. And and a negative shear means that this angle widens. And I get it. That can be a bummer because you're just like, negative shear means the angle gets bigger. But yeah, hell yeah. But cool. So we're ready to draw in a positive shear. And what we're doing is we're drawing in a positive, we want to show a positive strain. And then we want to show a positive strain. And then we want to show a positive shear. And then get an equation for that. Because if any of those three values are negative, well, then they'll just be a negative value in the equation, and it'll work out. So that's kind of the cool thing about doing that. Cool. All right, drum roll, please. A positive shear is going to take this rectangle, and it's going to skew it that way. And again, fix this location, and then this can be a fixed part, and then so it's going to rotate that way. You know what I mean? So you can draw them both in if you want to. But check this out. This point is going to be fixed, and this diagonal, even though this diagonal again is this rotated element, and we're interested to see if it changes in length, and because this smaller rectangle does move this way, hey, this point has to move over here. And so, hell yeah, looks like this line lengthens as well. So even just that, and it's good to even start with the basics of like, what we just did was move this over here and this line lengthened due to a strain in the x direction. We put a strain in the y direction. Guess what? This line lengthened. Hey, and then the last one, we put a positive shear, and guess what? This point went from there to there. Hey, it lengthened. So when we get our equation for at least the change in length of this line due to these three strains being positive, each of them are going to lengthen this line. And the neat thing about each of those is going to act independently, or we can assess them independently. The textbooks will say all of these three happen simultaneously. When we do put a load on something, when we stress something, and then have the associated lengthens, or like shortening or lengthening of it due to compression or tension, those things happen at the same time. But we can say, hey, let's just say it lengthens here and measure that change in length, and then associate it with because this is a perpendicular, this change in length is perpendicular to that. And I don't even think shear would be, I don't even think that matters. Yeah, I forget what, yeah, that's, sometimes I overthink things. But it's just like all these can be superimposed. So we find this change in length by having a strain this way, and so but no, let's talk about this, because the same thing with stresses. Stresses aren't free body diagrams because they're not forces. Forces are vectors. Stresses are called tensors, and so they don't function. Well, I mean, the definition of why they're not vectors, because I know nothing about tensors, but just the basics of like why they're not vectors is because tensors can't add using the parallelogram method. I can't have like a tensor in this direction and a tensor in that direction, so that's what we have. We have down, we have down and then over. I can't just add these. Here I probably could because they act on the same faces, but you don't know that. You know what I mean? The tensor is just a stress operating on an area. And because it has those two properties, both can be changed. So I can't just add these areas, because this as a vector would be a shear force, but only if it was the stress times the area. Alright, hell yeah. So I guess just in general, we can superimpose, these changes in length. So that's what we're going to do. We're going to say it's stretched in the x direction due to the strain in the x direction. And so this stretches to there. This point moves to there, and then so the length used to be here, and now it's here. And then so we're going to try to use as simple geometry as possible. So now let's get into that. So I'm just going to redraw this. And I'm going to try to make it as big as possible. You know what I mean? So let's get this. This is our initial rectangle. And what we're going to do is just rotate it up to here. So this goes to here, and now we have a rectangle that looks like this. Hell yeah. So this was dx, this was dy, and the same thing here. This is dy, this is dx. All we rotated this up an angle theta. We're interested in this change in length because our equation for strain in this now x prime direction, this is x prime, this is y prime, is going to be the change in length in the x prime direction divided by the initial length in the x prime direction. So that's going to be a delta x prime divided by dx, because that's what we have, this initial length. And then so all we have to do is find the change in length of this due to our principal strains. Strain in the x, strain in the y, and gamma xy. Hell yeah. So now we have a basis of what we're doing, and this is going to give us the strain in this direction. It seems like, hey, we want to know the strain in this y1 direction too. We'll get to that. But the wild thing is we're going to get an equation for this, and it's going to be a function of theta. And so to get the strain in this direction, all we have to do is just rotate this element 90 degrees more, and then throw in, so strain in the y is just theta plus 90. But like I don't, like my first go around, I didn't buy that. You know what I mean? I have to see it to believe it. So we're also going to rotate this element all the way to here. It's going to be something like this, this, and this, and we're going to go through that same process. But it's just the same thing that's going to happen. It's like, well, we only know what's going to happen in this direction, so a change in length in this direction. So we need to box those things in. So even right here, we need to box this in. And now, cool. So now this diagonal is part of this box. This box has dimensions dx sine theta, and it has dimensions dx cosine theta. All right, hell yeah. All right, so let's dive in. This is going to have a strain in the x direction, and so let's just draw that in, meaning it has a change in length in the x direction due to a strain. Again, strain is change in length divided by initial length. So the change in length is strain times the initial length. All right, so let's do this. So this change in length right here is what we're going to find, and that change in length is strain in the x times the initial length, and this is the initial length, dx cosine theta. And that's the deviation from the textbooks. They're going to use a longer length and then change. They're going to do two things. They're going to rotate this element up and then make it increase its length. Because all of this derivation has nothing to do with dy ever, you could just lengthen this to that dx prime, and yet dy won't come into play at all. So yeah, but I just think, I don't know, I think my method is better because you're taking that dx dy and rotating it. That's all you're doing. And then you're figuring out how much this changed in length and not making it a new, yeah, and you'll see in a moment how it simplifies way easier. Okay, cool. So because this point moved to here, you know what I mean? What we do is this. We treat this as your hypotenuse, and then just know that this is kind of your axes. You know what I mean? So this is my x prime, and this is my y prime. So if this is my hypotenuse, I move this way. I want to know how much it moved in the y prime and this x prime direction. And so there we go. So there's going to be our right triangle. So it moved this much in the x prime direction. I know the hypotenuse, and so now we got to play the game of like, hey, what's our angles of this right triangle? And so here's one where if I have this angle, and then I come up here, that's the same as that. And see how these pictures get really small. So I'm just going to do a line like that for theta, and then I can even say that this other angle is phi. It's the complementary to theta. If I knew the hypotenuse, This is the angle. The sunshine is shining on the sining, so the angle is shining on the sine component, where the cosine is this adjacent. So I'm going to take the length of the hypotenuse and then multiply it by the cosine of theta to get this change in length. So back up here, so our this is going to be the change in length in the x divided by dx. So our first value for change in length is strain in the x, dx cosine theta times cosine theta. And we just do this. This is cosine squared theta. You can just see that right off the bat. Now, this will have two parts where, we're just finding the top part of this equation, and then we're going to divide by dx. But look at this. This dx cancels that dx. So this is way simpler in the textbook. The textbooks, you would have a dx prime, and you wouldn't have this cosine. You just have the dx prime, so you'd be missing that cosine. But then dx prime divided by dx, so if we did the diagonal, you know what I mean? Hey, this dx prime, this larger, would be dx prime divided by dx. Well, you would say that dx divided by dx prime, adjacent divided by hypotenuse, has to be cosine theta. So therefore, if we saw this in our equation, we would have never mind. Reverse that. If this was dx prime, this a diagonal, then this distance would be dx, and then the lengthening of it would just be ex dx. So we would have just ex dx cosine, and then we would have to divide by dx prime. So dx divided by dx prime is cosine theta, and so that's what we would have there. Well, we'd probably have a dy divided by dx prime. In a second, we would use the dy part, and that's going to be synonymous with sine theta. Sorry, I just kind of rushed through that, because this method you don't have to do that. Hey, look at this. Our dy component is just a function of dx. So everything's a function of dx, and we're going to divide by dx. So it's just like simple. Like you just do all the hard work at the beginning or something. All right, booyah. So, all right, so that's going to be the change in length of that. All right, so that's that, and we're going to superimpose three things. That was going to be the change in length in the x due to the strain in the x, that initial one. Now we're going to take our box and it's going to strain in the y direction. So I'm just going to come up here, and then this is the change in length. Because this change in length isn't in the y prime or x prime direction, I'm going to treat it as a hypotenuse and then drop down, here is the x prime, y prime direction. So now I have a right triangle, and I know my hypotenuse. And again, let's figure out what the hypotenuse is. It's going to be the strain in the y direction times the initial length. And back here, what's change in length in the y direction? Strain in the y direction times the initial length in the y. This is the initial length in the y, and we have the strain, so strain in the y times the initial length, dx sine theta. That's going to be the length of this hypotenuse. The only thing we're interested in is if this this component of it. And so that component, we need to find our angles again. And didn't we say that, hey, we have a horizontal and then we have a positive theta? And that's also, not a positive as in if we're from the horizontal, our slope is going to be positive. Cool. And if we're from the vertical, a tangent to this will make our slope negative. And if we have a slope negative, here's our theta and there's our theta. So that's what we have here. We have a vertical and we have a negative slope, so this has to be theta. That's one way to do it. The other way to do it could be, let's try to find one more way to do this one. I could say that I definitely know this is theta and this is theta. So if this is theta, this is the complementary. And then I know that this is a 90-degree corner. So if this is 90, it has to have the complementary and theta. So that's another way to do it. It's nice to have 3 or 4 different ways to figure out. And that's why also when doing these proofs for this one, it's really nice to make this angle narrower than this angle is wider. And so you're complementary, so you can kind of see it. It's like, ooh, I can kind of see this is the narrower angle and this looks like the wider one. Even though it really takes about a 20-degree angle to really visualize that this is different than this. This is a narrower angle than that angle. But cool. And then so we want to know if this is our hypotenuse, this is the angle of theta. This is the sine component. So we want to know the sine component. And so that's going to be sine theta. The other thing you need to be paying attention to, the first thing we did is like, hey, if I lengthen this, the line lengthens. If I lengthen this way, that line lengthens. But if I did the opposite, if I came in here with something that was in compression, that's going to be negative strain. That's a shortening. Then this line is going to reduce. If I had a shortening to here, this is a hypotenuse. Drop down my, my coordinates for y prime, x prime. And then I can see, hey, there's my right triangle. And I would have a reduction. And here's the narrower angle. Or, use the Zorro to figure out that this is theta. And so in that case, I would have a, this angle would be reduced. But I can just throw a negative value in here. For the negative strain, that's going to happen, and we're going to have a change in length in the negative. And so this is still going to be, we're back to this one. This is going to be strain in the, that would be this one being a negative. Our strain in the x would be negative. This length would be negative ex dx cosine theta. We would have this component of it, which would be another cosine. And so you'd have negative ex dx cosine theta. And we just keep this as the positive. And in our equation, if it says, hey, we have a negative 250 times 10 to the negative 6 strain in meters per meter or whatever, then we throw in that negative value right there. And so that's the same thing as on our picture, doing it pictorially in that negative and shortening direction. All right, hell yeah. So we just did 2. We're almost done with this one. So this one in the y direction made our length longer. And again, it was strain in the y times the initial length from this equation. So we have strain in the y, dx sine theta. So that's something that I kind of got really used to, is just like, hey, if you're trying to find the change in length, always start with this strain in that direction and then multiply by the initial length. That way it's just kind of like this 1-2 punch. You're like, hell yeah, we're straining in this direction. That means my change in length is going to be the strain in the y, times the initial length, the dx sine theta. And then it's going to be the hypotenuse. I want to know how much of that is lengthening or shortening. I see that it is lengthening. We're going to have a positive value on that, and it's going to be the sine component of this. So hell yes, that's our next component. Strain in the y, dx sine theta. Obviously, it's sine theta squared. All right, hell yeah. So now for the for shear strain, we're going to see how that changes this diagonal. And again, don't think of it as a diagonal. Think of it as this thing is now rotated up to here. All right, sweet. So, but same thing. This element is going to be rotated up to here. We don't know how much it's going to change in this direction. That's what we're trying to find. And so what we're going to do on this one is and in this we're not, like right now, we're not trying to find the change in this rotated element, the change in angle. We're not trying to find the shear strain, which is an angle in radians, of the rotated element yet. What we're saying is that this rotation, you know what I mean, causes this length to lengthen. And so, and that would be the case even if we didn't rotate it at all. If I just had this dx dy, and I said that it, you know, in no rotation, you know what I mean, cool, and you wanted to know how much the diagonal changed. You know, that's one way to look at it, even though the diagonal is representative. The strain of this diagonal. So yeah, let's talk about this. So if we had the initial little chunk, this dx by dy, and we didn't have any rotation at all, and I just wanted to know how much this diagonal changed. You know what I mean? That is one geometric thing that you can think about. And even if you didn't know anything about the transformation equations or rotated elements, you're just like, hey, I have this rectangle, and I'm going to increase this length by this much. Hey, this is going to lengthen. I'm going to take this rectangle and then increase it this much. You know what I mean? This is going to lengthen. And then I'm going to take this rectangle and then do this with it. Cool, this point, as long as you fix this point moved to there. And so this lengthens. So this equation is going to be totally additive. If my shear is a positive value and my strains are positive, it's going to just be additive. Those three things are going to be additive. All right, hell yeah. And so, and then the other, you know, thing that I kind of spaced out on, but just even in the last moments kind of figured out is just like, well, yeah, no duh. So if my initial dx dy, like, rotates due to strain, like a certain angle this way, it doesn't matter whether I choose this as my differential element or if I choose something bigger. You know what I mean? If I had a bigger rectangle, that thing is still going to rotate the same amount. And so that still plays because we are going to rotate this up, and then we still have to work with this smaller rectangle that I'm calling dx sine theta, dx cosine theta, where the diagonal is dx. And that just makes sense because we started with a dx and dy element, and we rotated it up to here. Cool. And so, but now on this new smaller square, we're going to have this angle of rotation, and we're going to have that same thing over here. So let's do that. And what we're going to get, so this is an equation for arc length. And then this was my take-home point, like this week that I learned. Kind of the is if I have an angle, and you're using some sort of geometry, it has to be the angle of a circle. And you can think of it this way: if your angle your angle has to represent, you know, at least two lines, and those lines, unless they're theoretical mathematical concepts that go to infinity, which I don't know why you would be even, you know, in the real world, it's like, nah, it's like I measured an angle because I measured it between like two tangible things. And the lengths of these tangible things have tangible lengths. You know what I mean? Whether it's a meter or 1,000 meters. Like, still, these lengths are going to be tangible. And so, therefore, if I have any angle, it is associated with at least one of these lengths. And one of those lengths can be represented as the radius of a circle. So just the fact that you're saying, oh, I have an angle, not only do you have a circle, is like, well, you basically, you have two circles if you want, you know what I mean, and as many circles as you want as if you're taking different lengths from this. And then that's an easy way to think of arc length, because I swear I graduated without knowing the equation for arc length, and it just seems like a foundational one, and I don't know where it got lost or just why a teacher would say, like, hey, I don't even remember a teacher ever telling me this is the equation for arc length. I think it's just one of those things that you were supposed to look up in a textbook and have it be ingrained, and I just don't think it is. So this is one of those like moments where it's just like, oh, okay, And here's the easiest way to think and know why something is an arc length. So if I'm going to take this length, you know what I mean? I measured an angle between two lines, and then I know one of the lengths of the lines. And so I'm just going to make this into a circle. And so we did it, and guess what? This length is a radius of a circle. So you could say that these are synonymous. The length is the radius. And what do we know about a circle? I mean, a circle only has a few properties. It has a radius, and it has a circumference. You could say a circle has a diameter and a circumference, but those are completely related because the diameter is just 2 times the radius. That's a redundancy. And so really a circle can be defined as a radius and a circumference. And so sweet. So because, and a circle, well, I guess 3 parameters. It's a radius, a circumference, and an angle of like 360 degrees. Or an angle of one full angle. You could call it one rotation. You could call it 360 degrees. And we also call it 2 pi radiuses. And it's like, I don't mind spending 15 minutes every time you have to use radians to explain where this comes from. I guess it's as simple as this. If I have a circle and this is the radius, I'm going to cut a length of string and drape it around the circle, and I'm going to get to about there. And that is about 60 degrees. All right, hell yeah. And so this is about 60 degrees. It'd be cool if it just was 60 degrees, because then pi would be 3. But it's not. But anyway, just think pi. You should always think pi is 3 anyway. You know what I mean? And, but cool. So you get to there, and then you cut another radius of a string, and you get to, about another 60 degrees. And you realize that, hey, a circle, to get halfway around the circle is about 360. That's 180, 3 times 60. And so you get to about there. But you don't. You get 57.3 degrees. So you're coming up a little bit short. Another 60 degrees, another 60. And you're just a little bit short. You're short by 0.28 radians. So if I cut this up into about a quarter, I would need about a quarter more. And where does that come from? Well, what you're going to get is 6.28 radiuses. You know what I mean? So if you cut the radius into strings, you're going to need 6.28 of them. And so 6.28 is a 3.14 twice. So, 3.14 times 2 is going to be this, which is going to be 8, 2, and 6. You know what I mean? So, hell yeah, that's 6.28. And because this is 3.141, 5, this is a close enough approximation, 6.28. So you're going to have 6.28 of them, or 2 pi radians. In what? You're going to need 2 pi radiuses to go all the way around a circle. And so what we're going to say is that this angle is, if I just cut one radius and go to there, we're going to call that an angle of 1 radian. This is 2 radians, 3 radians. We're a little bit short of 180. 4 radians, 5 radians, 6 radians, 6.28 radians is a full circle. So sweet. The angle of a circle can be 360 degrees. It could be 1 full circle. It could be 2 pi radians, or 2 pi radiuses. 2 pi radians. Where it's just like this. We don't call this angle 1 times the radius. We just call it 1 radian. Where if you had the length of the radius and you draped it around the circle, that would be equal to that angle of 1 radians. So, so that's where this arc length. This arc length has to be 1 radius to have an angle of 1 radian. And so, hence, here's my lingo, is that radians are ridiculous or they're bizarre. So to make them into something useful, I just say radians times radius. And I'll even change my equations just to make sure they're in this form. Because radians times radius is arc length. And I don't even think arc length sounds like something normal, but hell yeah, it is, because it's just a fraction of the circumference. So if I had like this, if this was a radius of 1 meter, then this arc length would be 1 radian. This arc length would be radians times radius of 1 meter. That arc length would be 1 meter. Cool. So hell yeah. And if I had 6.28, if my angle was 6.28 radians, radians times radius gives me 6.28 meters, which is the circumference, because the circumference of a circle, and I always like to start with circumference of the circle is pi d. It's your diameter times pi. I think you would do that. You would measure a diameter, and then you would multiply by pi. So I would write it like this. I'm a big fan of rearranging equations into doing what you would do first. You would gather a diameter and then multiply it by a constant. But I get, you know what I mean? Because we have a linear relationship, you would be like, hey, the equation for the circumference must be some sort of constant times the diameter. If it's a linear function, like if we change the diameter a little bit, the circumference will change linearly. Then this would be your y is equal to mx plus b equation. So I'm okay with that, but I don't think at the end of the day people are thinking circumference, like circumference is pi d. I don't think they're even thinking this is a part of a linear equation. I think sometimes this is more useful. I'm going to go gather some evidence. Here's my tree. I'm going to go measure the diameter, and then I'm going to multiply by pi to get the circumference. So that's what we have right here. And we know that the circumference is 2 times the radius. So this is, I would do 2r times pi. So I would just rather write the circumference as 2r times pi, because again, that's kind of what I would do. Gather the information, here's the radius, I'm going to double it, and then multiply by pi. That's kind of what I would do. But I'm glad I, identified this as a linear equation. And yes, you would take a constant, you're relating two different things. Circumference is different than the diameter. Circumference is different than the radius. And so we need a constant to represent, to change that. Even though these are still meters on both sides, this constant is unitless. And in this case, it's going to be 2 pi r. And in this case, it's going to be pi. So we have circumference is pi times diameter. Here we have circumference is 2 pi r. So hell yeah. So the circumference of this circle of radius 1, which 2 pi times 1 meter, is just 2 pi meters. And so that's what we have when we're using radians. If I know the radius is 2 pi times the radius, then I know the circumference. And booyah. And this only works when you do radians. There is the benefit that we're going to see in a second of why radians were chosen. You could have just done diameters. You could have had a circle, had this diameter, cut that length, and then just get about a third of the way around, get another third, and get another third. And be like, hell yeah, there's going to be, and we're going to call that angle 1 pi. So this could have been pi diameters. Maybe just call it diams. You know what I mean? So you have pi diams, and then and which is a bizarre sounding thing. So what's the arc length? Well, that's just going to be diams times diameters. You know what I mean? So hell yeah. So you have pi diams, which is representing an angle, and that's kind of a unitless thing. It's going to be a proportion. You know, the angle is the proportion of the full circle. So that's the other thing, is like an angle is just a proportion of the full circle. So anytime you're dealing with an angle, it's in proportion to the full circle. You could have an angle that's more, it could be multiple revolutions, you know, but that angle is just, then it's bigger than the full circle, but you take that angle as a number and divide it by the number for the full circle, and then hell yeah, maybe you get 3.5 revolutions or something. In this case, you're always going to get a smaller number, like here's our smaller angle, and then the total angle for the full circle is this, and you get a proportion. And that for sure is a linear proportion. This looks to be, this is a quarter, this looks like... Alright, hell yeah. So I took a huge break. It was about noon when I left this little angle, and now it's about midnight. So booyah, but we still want to finish this. So I think I'm done talking about angles, but we definitely have to talk about how this angle is in radians. And, you know what I mean? So, and this is going to be the radius. Cool. So keep that in mind, that every time you have an angle, you know, it's probably associated with a length. You know what I mean? Because these two rays aren't just going to go to infinity if you got an angle. So sweet. Alright, so hell yeah. And radians times this radius is going to be this arc length. But this arc length is going to be a curved line. So now we have to talk about width strains and shear strains, normal strains and shear strains. These strains are so small, and especially with the normal strains, this little change in angle is so small that, check this out. So if I pivot this just like hardly at all, you know what I mean, to there, did you see it? That's a perfect tangent. You know what I mean? There ain't no curve here. And so, so there you go. So this curve, you can just assume does not exist, and the straight line is what we're measuring. This curve is the same, even though it'll be, yeah, I mean, if we took if this curve went to there and we said, hey, I'm going to drop a line up, and this is the x direction, well, sure, the curve is going to be a little bit longer of a line. But this straight line is what we're going to be just approximating. So hell yeah. So radians times radius is this length, and then it's just booyah. So we have, what's this length? Radians times radius. So this length is gamma in radians, that's the angle in radians, due to the shear, and the radius is going to be dx sine theta. Dx sine theta. Alright, sweet. And that's going to happen on both sides. So we talked about how shear is going to, you know, both angles are going to be the same. And definitely just don't forget about how truly you can draw the picture where this is not flat, where actually this increases by half of gamma, and then you would have the other half of gamma over here. So you would do that like this. I'm going to shift this one over that much, and then this line up that much, and then kind of square this off and connect those dots. So I'm going to come in here like this, and now you have drawn a perfectly sheared, and so this right here is going to be gamma divided by 2, and this is going to be gamma divided by 2. So each of these represents half of the total change in angle, but again, we can just pretend like we're fixing this location, and then what happens is that total length becomes gamma. So that's pretty cool. Alright, so over here you're going to have that same gamma, and it's going to be associated with this length. That length is going to be the hypotenuse compared to this y prime and x prime direction. So let's just say it went through that same point right there. And so if this is the hypotenuse, this is the y prime, and this is the x prime direction. And then here's my 90 degree. And what we're still interested in is the change in length. This dx used to be here, and now it's got this extra change in length. That's going to be this hypotenuse. Whoa, just a second. So what do we have here? Okay, so this is going to be, let's say, oh yeah, what do we got going on? Oh, so this is my little box. Sorry about that. So my original dx was here. My original dy was here. And we said we had to rotate that. And when we rotate that, well, actually, I already drew the change in x's. So here's my original dx. And then I think on here, this must be my original dy. Is that about right? I don't think so, because this value is dx. So hopefully, oh man, hopefully I didn't mess this up, because I wanted to portray that this original box was dx dy, and when we rotate it up here, it still remains like dx dy. But I'm gonna, it's been so long coming back to this problem, I kind of don't know where I'm at. But I'm still gonna call this dx right here. No, we're chill. We're chill. Because I got confused because of, we already did the shear. But hell yeah. If this is dx, that came down to here. This point right here to here, this was that original dx. When we, and then, I don't know, you could probably just say up here is the dy, doesn't really matter. And then so we're going to rotate that up. And then we want to know this change in length. Cool, because that would be the normal change in length in this x prime direction. That's going to give you strain x prime. Just the normal strain in that direction. That's all we're going to try to figure out. But we don't know anything about this direction. All we know is stuff about this direction. We know this, and we know this, and then we know this. And so from this diagonal, that's where I have boxed it in. And so cool, this is still dx to there. But then I make this little box, and my box kind of grew. But hell yeah. So now this box has dimensions dx cosine theta and dx sine theta. So this angle gamma is going to be radians times this radius, and we're going to come out over here. That's the only tricky thing about doing this proof, is that once you get down to this little triangle, it gets kind of small. But we're chill, so we have the hypotenuse, and then just go out to the hypotenuse and then start drawing in, you know what I mean, your actual new direction. So we have, here's the y prime, you know what I mean, and then let's draw the x prime. Okay, sweet. So we draw the y prime and then come over here and draw the x prime. You know what I mean? You do you. Oh, and then check it out, because you can do, so what we just did there was we did this, and we're just like, okay, I'm going to draw the x prime and then the y prime. And then I'm going to see what that gives me. And then come over here and do the same thing. X prime and then the y prime. And guess what you get? Like, here's your hypotenuse, and it can be the hypotenuse of 2. And this is kind of the parallelogram method. If I'm trying to start from here, and this is my resultant vector, the hypotenuse, we've called it the hypotenuse, you can go this way. And then I do, like, if this is a closed arrow, you know what I mean, just for kicks, I'm going to show the components with open arrows. That's kind of just my taste. And I can go this way, down the x prime, and then I can go in the negative y prime direction. Or I can go in the negative y prime first, and then I can go over in the x prime. So both of these will juice it out the same, you know what I mean? So here's your theta, and then your other angle is going to be that complementary. I'm just going to say that is phi. Cool. All right, so hell yeah. So even when you get, you know what I mean, a little bit, you know what I mean, hey, this is that, and what we're interested in is this change in length in the x prime direction. So that's going to be the hypotenuse that we found, and then the cosine. We want this length. Sun is shining. This is the sine component with this angle. It is shining on the sine component. The cosine is the adjacent. So we have hypotenuse, cosine theta. The hypotenuse is this term right here. So we have radians times this radius, dx sine theta. And I don't know, I guess I enjoy my teaching method because like life is just it's a huge juggle for all of this, and you're probably going to like forget it after leaving it for a year, for 2 years, for 3 years. So I really like to pick up all the balls, see if you can juggle them, drop a few, and then start picking them up again. And just kind of always going from scratch to where I might make where I'm a little bit slower, might make little hiccups. Hell yeah. And so sweet. So we have our last term doing this positive shear is going to lengthen this line. And it's going to lengthen this line. The hypotenuse is radians dx sine theta, gamma dx sine theta, and then we're going to have the cosine of theta. So this is my hypotenuse, and then the cosine component that rounds it out. So we have gamma dx sine theta cosine theta. Booyah. And so that's going to be the change in length. And because we chose to have these as dx cosine and this dx sine, and this to be dx, this is the original length. So strain is the change in lengths, cool, divided by the original length. And check that out. You just do that. You factor out that dx, and now we have strain in the x prime direction is strain in the x, the normal strain just in the x direction, cosine squared. And these are all positive. Positive, positive, positive. All those things make this line lengthen. Cool. And then we have epsilon y, ey, or the normal strain in the y direction, sine squared theta, plus gamma, or this is shear strain, normal shear strain in the xy. So this is normal shear strain about the xy plane. And hell yeah. And it's going to be sine theta cosine theta. Alright, hell yeah. And you're done if you just want to throw this into your calculator. If you want to use more circle, we need to get this something not in terms of a cosine squared. We need to get it in terms of like a 2 theta. Like a sine or a cosine, like just a cosine 2 theta or a sine 2 theta. That would be fantastic. Because the whole reason we're doing this is because we might be given, you know what I mean, a number like 1,000. Oh, sorry. How about 250 times 10 to the negative 6, strain in the y, 175 times 10 to the negative 6, and then a gamma. This is an angle in radians, and hey, like steel is 0.002. And that's going to be meters per meter. This is also meters per meter. This is going to be 0.00025. This is the max for steel. That's why you're going to have like 3 zeros. Because this is going to be a tenth of the max change in length that you could get out of this material. Even if it's steel, you can still just have a lower stress. Just, you're not going to try to take everything to the limit of factor of safety. But for steel, this is its limit. And so that's why you're going to see values of strain that are going to be like, hey, a tenth of maybe the limit of steel. So it's going to be an extra 0. So keep that in mind. And then just know that, hey, if I wanted to get this as 3 digits, I'm going to go 1, 2, 3, 4, 5, 6. And that's typically the game. You know what I mean? You're going to be 3 digits up to 4 digits. Like say, if you're doing the max for steel, this is going to be 2,000 times 10 to the negative 6. So just know that these shear terms can be anywhere from like, I don't know, even 10 to the negative, like 85 times 10 to the negative 6. That's 1, 2, 3, 4 zeros, 8, 5. But most of them are going to be 3 digits. It's going to be 0.000175. And just know your max is 2 zeros and a 2. It's going to be 1 or 2 10,000 or 1 2 1,000s. Tenths, hundredths, thousands. All right, hell yeah. So and you know what? We're gonna clean this up because it's not too hard to have these identities just in your back pocket, because there's only two things that you need to do or know. Like the main idea, and the reason I just went through that whole spiel was to say that our given values might be 250 and 175, but when we rotate this element, maybe we get up to like double that. Maybe we get up to 450 and 500. You know what I mean? And this is where, like, in the stress video, I wanted to know. You know what I mean? It's going to also be a function of what your normal stress is, because maybe, and the reason I went through that, sorry about this, so max for steel is 0.002 meters per meter. That means that if I have 1,000 meters, or 1,000 millimeters, I can lengthen it, or it did lengthen 2 millimeters. That's going to be 2 1,000ths. So that would be the strain that I would measure, see, or use electronic devices to calculate. Now, I wanted to know kind of what are general values for this change in angle. You know what I mean? Because it's not meters per meter. And so, yeah, what is that? Like, what's happening there? And so, but it's close, and you can imagine that it's close just because, hey, small angle just says, hey, if this thing moves this far, that angle is going to be proportional to this length. And so, yeah, let's look at this, because we have radians times this radius, which is the length initial, is going to be, and that's going to be the change in length. So you can really see that, hey, this shear strain as an angle is very similar to change in length divided by original length. And so you can see that the change in length of this was like very proportional to what we just drew it. Where the change in length of this angle is also very proportional to probably how we drew it. And you can see the direct similarities between strain in a normal direction is change in length divided by initial length. So for steel, the number isn't 0.002, but it's just double, 0.004. And this comes out of straight geometry. And so that's a good one to do, is just figuring out if the max change in length can be 0.002, what can be the max shear? Because what you're going to have happen is you're going to have this, and this lengthens. Let's say this initial square was 1,000 millimeters across. It can only go to extra 2 millimeters. And when it does, this thing is going to play out of an angle of 0.002 radians here and 0.002 radians there. And so that's a great problem to do. It's in the gearbook. And so then we have our total strain at max. Our max total strain for steel as an angle is going to be 0.004 radians. All right, hell yeah. And that's why I always use steel, just because it's one of the strongest and most used materials, and easily produced, and you know what I mean? Its strength comes basically in 3 grades: 50,000, 150,000, and train steel, or 100,000, 50,000, 100,000, and train steel in grade 8 bolts are 150,000. You know what I mean? So without doing very, very special things, like, hey, this is just everyday attainable, 50,000. It can be less. It can be as low as 30,000, or even just a little bit less. But hell yeah, 50, 100, and 150. So those in PSI, that's the strength in PSI, are pretty easy to remember. And 0.002 for a max change in length per the original length. That's the definition of strain. Those can be pretty easy to memorize. And if you get 58,000 psi and 0.002, your modulus of elasticity is always 29 million, which is a common number used in books. But, you know, these can vary, and different problems will have different values for them. But these match, because 58 divided by 2 is 29, and dividing by a smaller number moves the decimal 1, 2, 3, and so hell yeah, we get 3 extra zeros. 58 million, half goes to 29. So it's just kind of nice, even though 0.002 is a pretty small number, just to have one where you can kind of mentally do the math, taking a normally big number, dividing by a small number, and, you know, getting a number that's definitely substantial for E, 29 million, and then having some sort of understanding of why that is. Sweet. Alright. And the reason why that is because you have this. You basically have a change in length and force graph. Now it's proportional, where this is a change in length per unit length, strain, and this is kind of a pressure, a force per area. So that's what you have. And, hey, this can only be a max of 0.002. So where on this would 1 be? Because the definition of slope is rise over run. You know what I mean? And so if I went all the way over here, like, what would be my strength? Well, you can't do that. I mean, you can only lengthen steel to yield right here, and then we're going to come up here to 58,000. So it would be cool if you could stretch steel 100% of its original length, but you can't. That would be going out to, that would be the definition of going to 1. That would be a change in length of the original length. L naught is the change in length divided by the original length L naught. That would be 1, or 100%. And so on here we're going to get a slope that's like hella not moving up, going over very much, but then we go up a pretty big number. And so rise of 58,000, but our run is only 0.002. If we went over here and this just kept on going, well, I would have to multiply this number 500 times. I'm trying to get better with the mental math, because if this was 001, that's 1/10,000th, and I would have to have 10,000 of these. You know what I mean? And hell yeah. And then this would just keep going at this slope, and then I would have I would go up 29 million. And I would go over 1. So that's the definition of the slope of E. You know what I mean? Go over a distance of 1 and then go up 29 million. Or just go over the distance of 0.002 and go up 58,000. And then rise divided by run, we just went over that. 58 divided by 2 is 29. Another way to think of that is 58 divided by 1,000 is 58 million. But then we still got to divide by that 2. We get 29 million. Hell yeah. Alright, booyah. So we really need to, you know what I mean, at least chisel this one out. That was my whole goal, is to do kind of like the 3-hour, you know what I mean. And then the whole thing was like, hey, take the original square and rotate it. But then when you're looking at this diagonal, we still have to kind of box it in. That's the best part. But anyway, so we are going to... we're going to use the trig identities, and the ones that, I mean, the light bulb has to come off after you do these trig identities. But if you're doing trig identities, do this, you know what I mean? Do a kind of a wide triangle, and then bisect it, you know, right in the middle, and kind of do that twice, because there's going to be 2 of these. And you're just going to call these theta. They're going to be the same angle. This is the, I mean, obviously these could be different angles, and that's the general form for this, but for most trig identities, and these good ones, this is what you're going to do. So draw this, and then we're going to drop this down. Like, hey, this is going to be a distance of 1. That sucks, because what the hell is a distance of 1? You know what I mean? You could make it 100 and just get on with life. But cool. But it's nice to actually have something like this, because this is the length of a hypotenuse. And guess what we're going to find? We're going to find the cosine of that, of both these angles. So this right here is the cosine of 2 theta. And and this is the hypotenuse. So you could say this is the hypotenuse cosine 2 theta, and guess what? The hypotenuse is 1. Sometimes when you're just starting out in trig, that is very useful to actually label your hypotenuse, as a, and then you can call it 100%, and it'll still play. Anyway, so cool. So we have cosine 2 theta is this. And then all you have to do is just play the game of like, hey, if I have this, I could find the sine of it, or I could find this cosine. So that's what we're going to do. We're going to get the cosine first, and then take a pause. Now I'm going to say this length is my new hypotenuse. Cool. And now I'm going to drop it down 90 degree. If this is the hypotenuse, this is the hypotenuse cosine theta, right? And so and this is going to be the hypotenuse cosine theta. Hey, my hypotenuse to start with was 1. And this is going to be, so this is going to be 1 cosine theta. This has to be the hypotenuse prime. This hypotenuse is this. So, like, this is actually h cosine theta, cosine theta. And back, our hypotenuse is 1, or 100 if it wants to be 100, but hell yeah. So, cool. So you have 1. And then we're going to get the cosine theta. That's this component. Treat that as my hypotenuse, and then drop it down. And then this is cosine theta times cosine theta. So cool. So this distance right here is cosine squared theta, but we overshot. Hey, we just wanted to know this. This is cosine 2 theta. So we overshot it. So cool. So this one is, you're going to do the sine, and that's going to be this length. And it's very useful to know that, hey, we talked about how if this, so here's our axis. Let's say this is just x1, xy, and then here's our slope of theta, and it's going to be a positive slope on the xy plane, and then that's going to be from the horizontal. So here I have a vertical, and so this slope must be negative from the vertical. So cool. So this is going to be my theta. And if this is my theta and this is my hypotenuse, we just said this was sine theta. 1 sine theta, but then you have to get good at dropping the 1, so this is just sine theta. And guess what we want? We want to subtract this distance. Like we know this, we want to know this. This is cosine 2 theta. And we want to know it in terms of this, cosine squared theta, minus, and then so we're going to do the sine of this angle. So this is taking the hypotenuse, which is sine theta, and then taking the sine of that. So this right here is sine theta, sine theta. So cool. So this identity just becomes, hey, cosine 2 theta is cosine squared theta minus sine squared theta. And if you do this 10 times, that's it. You're kind of done. You can do it just in a whoop. But but you need to do this 10 times before you're just like, oh, okay, yeah, no duh, I see. And because this isn't even the ending point that people go for. Typically what people do is you go from here and you're like, hey, I want to just get this in terms of cosine and not even cosine squared. So you're like, well, how do you do that? Oh, my bad. I misspoke on that. You can't get this in terms of sine or cosine without doing a square root over the top. I guess you could if that was your goal. But hell yeah. So we're going to use the idea of Pythagorean's theorem that says if this is the angle theta, again, this is 1. This is going to be sine theta, cosine theta. Pythagorean's theorem says these sides, this side squared plus this side squared equals the hypotenuse squared. 1 squared is just 1, so we have sine squared theta plus cosine squared theta is equal to 1. If you're writing this identity and not drawing this triangle, I think you're really missing out. Like, this is one that, like, do this 100 times. Do this just 10 times before you're like, okay, I kind of got it. Because then the light bulb will go on. Wait a month and the light bulb will go off, but hell yeah. But every time that you do Pythagoreans, at least make it geometrical. That's the easiest one to show what's going on with geometry. And so, cool. And there's no sine squareds or cosine squareds on this, but we just know that this squared plus this squared is equal to that squared. So now what we can do, and then this is an equation, and I've talked about, like, my MO is like, cool, you got an equation with 3 things. Rearrange it 3 different ways. And so if you've never done that, and if you're not able to spit this out from memory, and then here's the way I do it. You know what I mean? This whole Pythagorean's theorem is to get the hypotenuse typically. You know what I mean? So I have a side, and I have a side, and I'm trying to get the hypotenuse. Hypotenuse is always the bigger number. These sides are always smaller than the hypotenuse. Sweet. So it just makes sense that I'm going to square this, and then add them together. So now, when we rearrange this, we're going to start with the hypotenuse and a side. So the only way we can start with a bigger number and a side and get the other number is to, like, do some subtraction. So we're going to take the bigger number. So the bigger number squared minus one of the sides squared is equal to the other side squared. And so that's going to be, so let's just do it from memory now. So if I want sine squared theta, I know that's the hypotenuse squared. You know, I can put that on there. Minus the other sine squared, the other side squared. If I want to know cosine squared, that's going to be the hypotenuse squared minus the other side squared. And then let's see that from you know what I mean. If I'm getting sine just by itself, I got to subtract the cosine. You know what I mean? And that way you're not just memorizing that of just like, okay, if I want to get the cosine by itself, I'm just subtracting the sine. Cool, that's algebra. And that almost sounded cool the way I said it. Anyway, so yeah, in algebra, you can trust because it is like a linear, you know, there's no quantum physics going on, you know, getting from point to point. Yep, and yeah. So that's I mean, I don't know if that's like, yeah, but that is kind of the definition, not the definition of algebra. Like, obviously, algebra, you can have little holes and a lot of funky stuff going on. But our whole deal, and I should have said this before, just get to the point, is that there's going to be a rotation where the strain is maximum. And we want to know that. Maybe it's just rotating this 5 degrees and whoa, you know, we're going to get a big number in this EX prime direction. We're going to want to know that. Because a material can only take a specific change in length, a specific change in angle, or a stress, normal or compression, or a shear stress. So those 6 values, you know what I mean, those numbers are what we have to compare in this when we're doing our analysis of things. And so, cool, we want to rotate the element through 360 and see which one is the biggest. And so what we do is we just take this equation, which is a function, it's a function of theta. So we can change theta by a little bit and then grab a value. Change theta, hey, a bigger value. Change theta, ooh, a really big value. Change theta, hey, a smaller value. You're like, oh, guess what we just found? Maybe we found the biggest value. And you should do that. Throw this in Excel. Just use the equation right here. Put it in your calculator. Find the biggest one between 0 and 360. You know what I mean? And if there's a couple, maybe we're going to have some, like obviously, if we get up to here and this is the max, well, maybe if we rotate 180, well, that's going to be in the same direction. So yeah, we might have 2 maxes with a 180-degree rotation. And it's that kind of playing around with things that makes, when we do differentiate, when we say, hey, I want to just do a different, I just want to change this equation, I want to change theta and see how this is changing. And when I change theta incrementally, and I see that this at some point stops changing, well, I either have a max or a min. So when this is 0, when I go from here to there and I just have no change in the graph, 0, then I'm at a low point or a high point. I don't know if it's a low point or I don't know if it's a high point. But hell yeah. So that's what we're going to be doing. All right, sweet. So So now let's take a look at what we're trying to use trig identities on. This cosine squared we want to get in terms of like cosine 2 theta. Because we can differentiate, I can do d theta of the function cosine 2 theta. Hell yeah. You know, little chain rule, I mean little bit of u sub, you know what I mean, it's just 2. You know, graph out the cosine. Cosine's going to start here, go there. And it's going to be, the differential is going to be a negative, you know, because this slope is negative. But it's going to be sine. When this is 0, slope is 0. So when sine is 0, it's 0. So this is going to be 2 sine 2 theta. You know what I mean? So hell yes, that's the differentiation of that. And booyah. But who knows how to differentiate cosine 2 theta? I think the only way to do it is actually go through this process. Or just graph it on your calculator. But yeah, so sweet. So let's finish this identity. So we found that cosine 2 theta is going to be cosine squared theta minus sine squared theta. And we're going to sub in. And now we can just do this from memory. Let's just say this has to be 1 minus sine squared theta, right? You know what I mean? Minus sine squared theta. Cool. So we have 1 minus 2 sine squared theta is equal to cosine 2 theta. Now what we want to do is just get this by itself. Let's just bring it to the other side and keep everything like it is. So we have positive 2 sine 2 theta. This is, my bummer, you know what I mean? So we have positive 2, this is sine squared. And let's do a couple steps at once. So we get this to the other side is equal to 1, and let's get that to the other side, minus cosine 2 theta. Now, let's get sine squared theta just by itself. Just divide everything by half. So this is going to be half. But yeah, the biggest mistake you can do is not divide both of these by a half. So there you go. Because worse, they'll do this. And it just might, you still might make the error of not dividing both of these by a half. But hell yeah, that you won't go. Alright, we got some more juice. And, booyah. So when I see a sine squared theta, I can throw this in. Alright, now same thing. Cosine 2 theta was equal to this. So now I'm going to sub in sine. So we have cosine 2 theta is equal to cosine 2 theta minus. Now what is sine squared theta? It's going to be the bigger hypotenuse minus one of the sides. The bigger hypotenuse is 1. Minus one of the sides is going to be cosine squared theta. That gives us this side. So this squared minus this squared gives me sine squared theta. And I just factored out the negative just so you can, we're just dealing with the sine squared. Negative comes back in. And what are we trying to solve for? We're trying to get this by itself. This is going to be negative 1 plus cosine squared theta. So now I'm going to try to solve for this. Let's get everything to the other side. Oh, no. My bad. We have two of these. This is positive cosine 2 theta. So we're going to have 2 of those cosine squared thetas. Sorry, this is cosine squared theta. We're going to have 2 of these cosine squared thetas. That's 2. This negative 1, let's get it to the other side. This is going to be 1 plus cosine 2 theta. Divide by 2 everywhere. I'm going to have, and then let's just switch it around. So we have cosine squared. So this, I'm isolating this, dividing this by the other side. So that's just be 1/2 plus 1/2 cosine 2 theta. Just did 2 steps. Just divide it over here, and then just switch the equation. All right, booyah. So that is our other identity. Now we're not done because we got, you know, I mean, we used this to get, hey, these two. But none of it's sine theta, cosine theta. So if you ever see sine theta, cosine theta, the light bulb should go on to do this. And so if this was the other triangle I had, and I want to find, and this right here is 1. So this is going to be 1 sine 2 theta. So this is just sine 2 theta. This length all the way right there. Okay, sweet. So this might be a little easier because check this out. this hypotenuse dropped down a 90 degree. This is going to be sine theta. And then I'm going to make the vertical. This is theta. And then I'm going to go, hey, this is the, so this hypotenuse, this is our new hypotenuse. So we have sine, this sine of the angle. So this is sine theta. It is our hypotenuse. And we're going to take the cosine component of it. This is the adjacent, and that's going to give us that height. So this right here is sine theta, cosine theta. Same thing over here. I'm going to do the cosine. I'm going to get this length right here. That's going to be cosine theta. Because this is 1. This is going to be the cosine of the angle times the hypotenuse of 1. So this length is cosine theta. Then I'm going to take the sine. I'm going to use this as my hypotenuse. Use this as the angle. And take the sine component of this hypotenuse. So this becomes cosine theta, sine theta. So hell yeah. So this full height of sine 2 theta is going to be sine theta, cosine theta plus this term, cosine theta, sine theta. Doesn't matter which way these are arranged. They're the same, and we have 2 of them. So we have 2 sine theta, cosine theta. We want this by itself, so let's divide both sides by 2. So we're going to have 1/2 sine 2 theta is equal to sine theta, cosine theta. All right, booyah. So now we can sub it into this equation. We can say this is, so strain in the x is going to be, the normal strain in the x are, and then here's all of our identities. Cosine, so that's going to be a 1/2 plus 1/2 cosine 2 theta. Now we're going to have strain in the y times sine squared. So this is going to be 1/2 minus 1/2 cosine 2 theta. And then we're going to have plus the shear strain in the xy plane times this identity, which is 1/2 sine 2 theta. Hell yeah. And then you just get to do some simplification. I'm going to have a half of one of these and a half of one of these. So what they're going to do is like, well, they're going to factor out the half, which you can do that like just 1/2, and then you'd have EX plus EY. But they're just doing it all in one step, and they're just going to do divided by 2. So that's factoring out the half. You know what I mean? One, you can FOIL in the EX. So we have an EX here, and then an EX here, an EY here, and an EY there. That's another way to think of it. And then we have half an EX plus half of EY. And that's the same thing as EX plus EY divided by 2. So that's how you're going to see it. Then next we're going to have a EX plus EY plus EX plus EY. We're going to factor out the 2, and we're going to factor out a cosine 2 theta. So that's how you're going to see that. And then this is just going to be the shear strain in the XY plane divided by 2. Factor out the 2, that's it. And hell yeah. So now this is the transformation that you will see. So this will give you any strain with any rotation of the angle. And so this is where, because I kind of have to go to bed at some point, you know what I mean? So this is where they, just say, hey, rotating this thing all the way up to where the x prime direction, does this make sense? Because if I rotate up to here, it'll give me the strain along this line. You know what I mean? And the strain doesn't have to be thought of as a diagonal. It can be thought of as this, you know what I mean, this rectangle rotated up to there. I want to know the elongation of this rectangle. That is going to be normal strain. This point is going to move to there. This point is going to move to there. And I think that is more clear than just not doing that and just saying, hey, the length of this diagonal changing is the same as rotating that element and then having strain in the normal. But taking this whole face and going there, that makes sense. That's strain in the normal direction in the x prime direction. So, and that's going to be at this angle theta. Well, can't we just vary this angle to there, and we're just going to keep continuing taking this rectangle. And when we take this rectangle all the way over to here, we're going to have that same rectangle there. And the equation is going to be theta to there. And guess what we're going to get? We're going to get the elongation about the x prime direction. So it's going to elongate that way. And then, hey, and this is that length. It doesn't have to be thought of as a diagonal. That's all I'm saying. And guess what this elongation divided by the initial length, what is this strain? This strain is the same as the y prime direction. And so all we've done is just rotated an angle like to here. And so this angle is, just theta plus 90. So when I say that this is rotated here, and guess what? Guess what? Because you're like, hey, this length is smaller. Doesn't matter because strain is proportional. Strain in this new x prime direction or this y prime direction is going to be the change in length of this line, maybe it only changes there, divided by the length of this line. Well, a small change in length, then it's kind of a shorter length. Compared to if we rotated this all the way up here and we had this shape, hey, this is going to have more change because it's a bigger length. But the strains are going to be the same. If I rotated this whole thing up, I would have strain EX prime, and that's the value I'm going to get. And that's the same thing as just rotating it up to here and then finding the strains right there. And so we'll see how far I get tonight. But, I mean, you can do that too. You don't have to rotate it all the way. If I want to find just the strains in the y, hey, make a little square element, that encompasses, cool, it's a diagonal, you know what I mean? But we squared it off, and we know that this is going to have a strain in this direction. And so you can either take it this way and say, hey, this line is going to be now over here. And you don't have to even go that direction. A strain, you could go halfway in both directions. That would be kind of bizarre and make the math twice. But or you could just say you could go in this direction. A positive strain is just lengthening this element. So if I go here and here, hey, this point is now there. And guess what? Like this diagonal lengthened. And this diagonal of this little square, it's just like, why are we finding a diagonal? Why are we finding the change in length of the diagonal? Well, hey, check it out. That is that initial rectangle. Taking this initial rectangle, rotating it, and all I want to know is how much it changes in this direction. That's positive strain in the x prime. Even though the x prime direction is that way, I mean, doesn't matter. If this lengthens this way, that's the same thing as just shifting it here and then lengthening it that way. And so you get to play around with, what diagonal you want to lengthen. I make this little box, and that's where, coming back to this all day, I thought this was cool. Like, let's say this chunk of paper is, a little stamp. You stamp it on the bridge. And the bridge, like at this chunk, is going to be very similar. Like, I'm going to have a normal stress in these directions, and so I'm going to have a lengthening in this direction. So I'm going to have a strain that's going to make it lengthen, and then I don't know, let's say I just have a strain that makes it lengthen in the EY. So that's positive, this is positive, and let's just do those for now. And so it doesn't matter if I take this. The strain here will still be proportional. And let's say it's half, you know what I mean? So the strain here was half. Take this shape. Okay, the strain here is half. You know what I mean? Because strain is such a small number, that's a pain in the butt. But hell yeah, you can do whatever you want. And now let's take this triangle. It's taller than it is longer, but still, the strain in this direction is still half. You know what I mean? So there you go. So this would be strain is 0.5, and the definition of strain is change in length divided by initial length. The initial length, let's say, is a length of 2, and this is 1 and 1. Cool. This strain is 1. And does that make sense? Our change in length is 1, our initial length is 2, strain is 0.5. And I think no one ever does what I just did right there, and I think it's very useful because the human mind can't tolerate small numbers, like especially if imperceptible. You're just like, going back to that strain. If I really did have 0.002 and this was a number line, this right here would be 58,000. And then, and after 58,000, you just have, it doesn't take any more stress and it's just plastic, and then breaks. That's a very simplified model. But it for sure does not look like this. Like, you'll see it drawn like this, but the slope, a slope of 29 million, we can just do that like right now. I'm just going to go 29 times 10 to the 6, x, and then zoom 6. Cool. Hey, look at that. Look at that slope. You know what I mean? Hey, it looks like that, doesn't it? Sorry, I'm getting all feisty. But booyah. No, I'm just feeling good. You know what I mean? I feel like no one's gonna watch like long videos. But like I said, once you can't breathe the air, maybe you will. I have no idea. But I'm just enjoying learning and teaching and learning how to teach and teaching how to, all that jazz. But hell yeah. So, and material mechanics is one of those where the thing that got me the most that I'm not even going to cover, and I probably already did, is I just can't cover it though because it's a little bit messy. Is if I did have this change in length, even a strain in the x, and this thing is now over here, guess what my new angle is? It's theta minus alpha. I'm going to say this is alpha. That's the next thing we're going to get into. So when I do my, if I call this the hypotenuse, well, it's no longer this original angle theta. It's going to be theta minus alpha. So, and that's the bummer about this book. It'll say, hey, we're deriving this from small angles. But let's say you really do want to find the shear of a chunk of rubber. Like, potentially you might have to use theta minus alpha, knowing that this changed in length. And if I'm actually trying to find the true change in length of this in this direction, we're just saying the change in length is if this line did not rotate down. If this line was just still in this direction, hell yeah, hypotenuse. And then here's the cosine. But you can see it's not, this line is not up there, it's down here. And so enough said on that, but all you need to know is that these angles are so small, and that's where that comes in. But I think the hardest part is to when you're just like, maybe you don't know when to use the real numbers or when to see that the small numbers don't matter. You know what I mean? So, cool. All right, so we have, the reason why we showed you this rotation is because if I rotate an angle of theta plus 90, and I throw this into this equation, Ex prime is Ex cosine squared of theta plus 90. And this is what the textbooks do, because it's rigorous even just to get to that equation. And so, yeah, this will be good, because then I'll have a kind of a stopping point once we get to here. Plus Ey sine theta cosine theta. And maybe we will. It's good for me to find stopping points, because videos get too long anyway. But tomorrow, and or for the next time I do a sesh, I'm going to long play hey, what is the shear? We didn't talk about what the shear strain, the change in angle of this, like this element's given. Hey, it's going to change in length in the x, it's going to change in length in the y, and this given element with a 0-degree rotation is going to do this. Those are the three things that are given for this problem. So when I do rotate it up to here, you know what I mean? Hey, this is going to do that. Well, sure, this is going to do that because hey, this is we're interested in two different things. We're interested in this. This is going to do that. This part. And so, hell yeah, it's going to go, and this is going to be positive shear. Like, hey, this is going to go this way. And so that makes this line also go into, damn it. Positive shear is when this, squeezes up into this first quadrant. You know what I mean? So if this squattens out, and this angle gets bigger, that's going to be negative shear. That would be negative x1, y1, or negative x prime y prime shear. So yes, so my bad. So when this element, given the normal the I don't know why shear strain, when we're given the shear strain just in the x y plane, that is going to cause this, the rotated element, hey, this line is going to play out that way. So we're interested in the rotated element at theta and seeing if it squishes in and has positive shear or, hey, squishes out. You know what I mean? If this line angles this way, that's going to be negative. And so this does that. And when this goes this way, same thing. This line goes over here, and then this angle happens. And then when we go in this direction, well, hell yeah. That's gonna go inward. So that's gonna be positive shear. So we're gonna have two negative components and then one positive. And but shear is when we have if this is our rectangle, hey, this is two things are going to happen. This is going to go this way, and then this is going to go this way. And then we're going to have that peaky diamond. And that's going to be positive shear. We're going to have some sort of angle here, and then some sort of angle here. And only from this derivation, this isn't going to be the same. This is going to be different than that one. So we're going to call this alpha. And it's a bummer because we're going to say, hey, a positive rotation clockwise in the counterclockwise direction is going to be positive alpha. And then we're going to say from the horizontal, if we rotate this way, that's going to be positive beta. Both books do that. And it's an actual bummer because then you have to go back and be like, well, you know what I mean? This is positive shear. That's positive x1, y1, x1, y1 shear. But this, if I just did beta in this direction, that would be negative x1, y1 shear. So what we have to do is take alpha minus beta, and then guess what? That gives us the x1, y prime, x1, y1 shear. And so again, at a different date, we'll do that one. But that kind of gives you a good intro. So let's finish up with this, because that's the other thing, is what if I just want to solve for the, let's say I just want to solve for EY prime. We'll do, you know what I mean? Treat this as your dy length, and then treat this as your theta, and this length is dy cosine theta, this is dy sine theta, and hell yeah, just do your normal changes in length. We're just going to have, and even if you went this direction, normal in the x, this point right here is going to be right there. So this must lengthen, and we're going to lengthen hypotenuse, and then, here's the y prime, here's the x prime. So this right there is the component of my lengthening. Do that in the y, you know what I mean? And then find that lengthening. If I come up here, y prime, x prime, so then, hell yeah, that component's my lengthening. And then do this little thing in the shear. I'm going to go this way. So if I do that way on both, hey, this is fixed, but this one moved over there. Radians times radius, gamma times this length is this, but it's a hypotenuse, and we want to know what this length is. So there's my x1, y1, and I want to know that. So here's theta right there. So that's going to be radians times this radius, and then we want the sine of that sine of the angle, you know, times that radians times this radius, which is dy cosine theta. You know what I mean? So it's just good to be able to have a fluidity. But the take home, like the only reason I'm making this video is just like you can rotate up an actual rectangle, and none of the books do that, and it is maddening. And then you can rotate this rectangle up where it still has dimensions dy and dx. And then, sure, like I'm interested in this length. That would be the, you know what I mean? If this whole rectangle increases in length like this, that's going to be strain in the y prime direction. And so, you know what I mean? And I could do the same. I could come over here and do that same box. You know what I mean? So this is one where you could do this problem in like 10 different ways. And that's my goal, is to be like, hey, let's just rotate it up here and then do my box right here. And again, back to that one sheet of paper. I don't really have it. You know what I mean? Hey, like this is the x, this is the y, and then we have shear. And so if I draw a box over here, it's going to go this way. If I draw a box half the size, it's going to have the strain proportional. If I draw a rectangular box, well, you know what I mean? Let's box that in back to a normal box that has a component. I can find its component in the x and component in the y. Strain is just this change in length. Like the strain, if this box changes in length to here, that is due to the strain. And again, that strain is going to be the change in length divided by initial length. Cool. And we can rearrange to figure out what that change in length is. Change in length is that strain times the initial length. So right here, if this initial length is, if this is dy sine theta, so I'm going to have dy sine theta is my initial length. And I know that we're given the strains in the x. So strains in the x is how much this length changes. Change in length is strain in the x times dy sine theta. If that's that change in length, I know that's not in the x1 or y prime. I'm interested in the change in length in the y prime, so make this your hypotenuse, put in your other coordinates, and we're going to have theta here, and so we're going to have a sine theta of this. So we're going to have sine theta, and you're going to have... Alright, hell yeah. So then you just have ex dy sine squared theta. You know what I mean? And then do the same thing for the y direction. You're going to have this increase in y. We know that's going to be strain in the y times the initial length. You know what I mean? So it's nice to kind of memorize these equations. If this is strain, again, we're going to say change in length is strain times length initial. Those are the two you're going to use. You're probably not going to find length initial, which is change in length divided by strain. But for sure, this comes up so much in this proof, where you're just like, hell yeah, if this changes in length up there due to the strain, what's that change in length? Well, the equation is, change in length is the strain in that y direction times the initial length. For here, it's going to be dy cosine theta. Hell yeah. That is not in the y prime or x1, y1, x1 direction. So this is my hypotenuse. Make a right triangle in those two directions. And we're interested in this y1, which is going to be cosine. So we're going to have ey dy cosine theta. That's my hypotenuse. And we're going to have cosine theta. So we have hypotenuse, cosine theta. And that really goes back to those trig identities. That's why if you're doing this proof, hell yeah, for sure, you know what I mean, do these trig identities. Because we're going to, we can this is, sure, we've already done those. So here's what we're going to end with, because here's what they do in the book. All they do is like bring up a diagonal, don't even draw this in, change the length of this diagonal, and cool, you know what I mean? You're like, you know, like exactly, this is all they give you, you know what I mean? Cool. You had an original length, you're going to rotate that up. For some reason, you're going to increase that length for no apparent reason. And then you're not even going to show that it's associated with a rotated rectangle. And, yeah, so it's kind of a bummer. And because this is your initial length, dx prime, like you're going to have dy divided by dx prime. What the hell is that? Then you're going to have to come back here and say, hey, this is dy. And dy divided by dx prime is sine theta. You know what I mean? Sine theta is opposite over hypotenuse. So it's just like one extra step. And it doesn't show that rotated element. And then at no point would you feel confident just to rotate this element another 90 and then feel like that equation would be working in this y prime direction, that you would get strain in the y prime just by saying that strain in the x prime theta plus 90. So, yeah. And then so that's kind of what we're going to finish with, is to show that here was the strain in the x prime. You know, it's a function of theta. Oh, yeah. And then we're going to, sorry about this, and this is going to be theta plus 90, and then theta plus 90. So sorry about that. And if we do that, so this should be just sine theta, this should be cosine theta. But when we rotate up an extra 90, we got to figure out, that's why, yeah, you can do this right now, but we already put in the equations to change it. So this is our fully changed transformation equation. This is ready to differentiate. We kind of talked about that, the differentiate with respect to theta, you know what I mean? Just pretend there's just a theta in here, but then you got the u substitution, so you bring out a 2. Or just go through the u substitution. If you're not solid on that, it's good. That's a baby step 1. That's the one that even I would have to do after a month of not doing u sub. So, yeah, I actually want to make, I mean, when I do I don't make specific videos, but yeah, when I do u substitution, even if it's small, like I will crush that out. You know, same thing as like taking an equation and seeing that it's 3 equations. That's the same thing that I do with u sub, because yeah, the differential, like you should always do a differential is like, hey, I'm going to change, you know what I mean? And it's typically like this, x, y. Cool, this is like 1, 2, 3, 4, 5 in seconds or something known. This is your independent variable. It's always going to be those increments. Now, this is your dependent variable. It'll still have increments, but this is like, hey, I've got 2 apples, I can make 1 pie. Maybe if I have 4 apples, I can juice it out and get 3 pies, you know what I mean? And then you get some sort of, function. But hell yeah. So you always got to treat differentiation as like, hey, I'm going to change my independent variable just incrementally. And as I change it from here to there, I'm going to see what this does. This could change none, could change hella, and it could change negative hella. Or it could just change a little or negative a little. You know what I mean? Sky's the limit. I could just move this incrementally, and then the next time I move it incrementally, it's going to change something. You know what I mean? So that is a useful way to look at a derivative, besides just calling it the slope of a function. All right. So last thing, when we throw in this equation is what we're going to go theta plus 90. And this was not trivial for me. And so I actually think we should probably start out with that other equation, because it doesn't... yeah, where are we at? Yeah, it doesn't matter which one you start out with. I mean, once you get to here, you've done it. You can throw this in your calculator. You know what I mean? Theta, theta, theta. And so let me rewrite this one again. So we have that strain in the rotated direction in that x1 direction is the normal strain given in the x direction, cosine squared, and we're gonna try to do the theta plus 90 plus EY sine squared theta plus 90 plus the shear strain in the xy plane sine theta plus 90 cosine theta plus 90. All right, so we have some different terms here. We have a sine, we have a cosine, and we have a sine squared and a cosine squared. So this is how I would do this one. This is how I've been doing it this week. I'm just going to pick an angle of about 10 degrees. Cool? And then I'm going to say, hey, let's do this one. And then these I'm just going to call theta for now. So what's cosine and sine of theta? So this is going to be the sine of theta. This is going to be the cosine of theta. Cool. So now what we want to do is rotate this angle 90 degrees. So that's going to be perpendicular. And now this is going to be 10 degrees. Like this is 10 from the horizontal, rotating 90. Hey, this is going to be 10 from the horizontal. So I know that, hey, isn't this synonymous with sine? And isn't this length right here synonymous with cosine? Well, sure. But we have to say this full length is theta plus, theta plus 90. This is going to be, this whole angle is 90 plus 10, 10 plus 90. And when we rotate farther out to here, my sine component is still the vertical. You know what I mean? So over here, my sine component is vertical. My sine component, no matter where I am, is going to be the vertical component. Okay, so this right here is, right there is sine theta plus 90. And isn't this similar to cosine theta? Yes, so there you go. So I can say sine theta plus 90 is cosine theta. All right, so now I want to find cosine of theta plus 90. That's going to be the horizontal component. So that component, and this is going to be negative. This is a negative component. If I do theta plus 90, cosine theta plus 9, I'm going to get a negative. This is going to be the same as this value. You know what I mean? And so this is sine theta. But this is going to have to be a negative. So now let's write it out. So the cosine of theta plus 90 is going to have to be a negative. And it's going to be negative sine theta. Hell yeah. And then, once you do this, 10 times, maybe you're just like, okay, now I remember, sine theta plus 90, no sign change. I'm going to go from sine to cosine, and I kind of wrote this in the wrong direction. Cosine theta is equal to, I don't know. You write it however in whatever direction makes sense to you. And then we're going to have negative sine theta is equal to cosine theta plus 90. Because that's what we have. Right here, I'm going to have a sine theta plus 90. That just goes to cosine theta. And then here is going to be a negative sine theta. We have a cosine theta plus 90. That's going to be a negative sine theta. All right, how about cosine squared? So we're going to come here and we're going to square this. If I square this, I square this. So this is just going to go sine squared. And then how about this one? Squaring this. If I square this, the negative goes away, and I'll just have cosine squared. So hell yeah. So that's going to be, the strain in the y is going to be EX sine squared theta plus, and this theta, that we're putting in is just this theta. But it's going to give me the strain in that in the theta plus 90 direction. But we already we don't want it theta plus 90. We just want it simply if I rotate up to here, But that really does show something. What does that show? That shows oh, you know what I mean? So we have two things going on here. So this is the strain in the y prime. Yeah, that is confusing. This is the strain in the y prime when we just rotated this angle up theta. And what we first solve for is if we rotate this angle up theta, we for sure have this equation. And we said if we have this equation, we can just rotate that theta plus 90 and get that shape over here. But for whatever reason, it just feels nice to be like, well, I want to input the same theta. I want to just rotate this up theta and get this strain and this strain in terms of this angle. I don't want to get this in terms of theta and this in terms of theta plus 90. That's a simpler way to do it. I mean, because once we get this equation, you just throw in theta plus 90. But what we, and even right here, we're on point to find this strain as a function of theta. Like right here, I did not write theta plus 90. And so this will give me the strain, the change in length divided by this initial length, you know, in terms of theta. I was already en route to do that, and we'll do that tomorrow. I want to do some speed runs through here. I think that would be very useful. But even this long video, because there was a moment I was just like, I could not figure out their logic. Like even this one, I was like, okay, sweet, you did a rectangle. Why didn't you rotate it? You know, I see you have this diagonal. Why didn't you just rotate the rectangle and have two rectangles on this page? But I think the second you do that, you got to do my style, and then kind of box in, like bring this rectangle up here, and then box it in. You know what I mean? And you would, you know, this rectangle would be right here. And so then you would take this, you would box this in, and it would just make it so much. And then this would just be dx, and this would be dx cosine theta, and then this would be dy. And it doesn't even have to be dy sine theta. I mean, well, it wouldn't be. It would just be dx sine theta. So now everything is just in terms of that L naught length. And so when you find strain, and I don't want to be writing on this, but if you find strain, it's just going to be change in length divided by that initial dx length. And this is all just going to be function dx, cosine sine, you know, function dx. All those terms are function dx. Dx is cancel. So it's just, that's the way to do it. Take this element, rotate it. Cool. Sure, you're finding a diagonal, but it would make sense to call that diagonal dx, drop down a box, call that box dx cosine and dx sine. And it just spells itself out. There's no reason to do it otherwise. And when you find this angle theta, just know that hell yeah, like this from the vertical is also theta, and then we're going to drop down this box. And guess what? This is dy, so this is dy, this is theta. This is dy sine theta. This is dy cosine theta. I can go through all that jazz, you know what I mean, to find the length of dy. And so the strain in this y1 direction, y prime direction, is just the change in lengths, you know, in that y prime direction, divided by dy, the initial. And this is just all functions. It's going to be dy. It's going to be strain in the x, dy, plus strain in the y, dy, plus gamma. Hey, guess what? Gamma, dy. Dy cosines and sines. But that dy divided by dy is just going to cancel out like that. Compared to having a dy divided by dx prime or a dx divided by dx prime, it's just a little bit more hassle to see that this is sine theta and cosine theta. It's good to do it that method, but it's just, I feel like I've, you know, found the magic loophole. Alright, so sweet. Yeah, that's why I really got into this video, and that's why I will do a lot of speed runs. Hopefully, you know what I mean? Kind of just do the speed runs to go all the way through. Because this video is so long, and we didn't even get, you know, x prime, y prime, is just because, I don't know, I think you'd want a freshie, you know what I mean? And then we can just dive right into that. But we did do this, hey, theta plus 90, and we figured how to get that as a function of, yeah, I don't even know where it is no more, but yeah, so we started writing it. So strain in the y prime is going to be ex sine squared theta plus ey cosine squared theta plus strain in the xy, and now we just have cosine theta and then minus sine theta. So this is going to be minus, and then I'm just going to go sine theta, cosine theta. Hell yeah. And then because these won't change signs, you know what I mean? This will just go. So this is the only thing that really changed on us, just that negative. And then so keep that in mind, because when we did our trig identities, alright, hell yeah, so last leg. So when we did our trig identities, we got this, and this is kind of the classic transformation equation. When we do Moore's circle, we're going to plot this, ex prime, and then we're going to plot in the downward direction, and we'll do that at a later date. And this is going to be divided by 2. But anyway, check this out. This is going to be, this is like a ex minus ey, so we have ex plus ey divided by 2. It's always the midpoint. You know, this is going to be the midpoint of a circle. And then, you know what I mean, the other things that are, oh yeah, I can't get into that. Sorry, I will hit a brick wall. Yeah, it's a skill to pick out an equation and pick all the things that are going on, like graphically, just like that. But all we're going to do here is we're going to get this in terms of theta plus 90. But we have something different. After we did the trig identities, this is a 2 theta. So let's go back to this. This is where I messed up, and I couldn't figure out why I was getting a sign change. Let me drink some water. Alright, so I'm still going to use that 10 degrees. Well, that's a little bit bigger, but check this out. This is going to be cosine 2 theta plus 90. Okay, FOIL this in. So this is going to be cosine of 2 theta plus 180. So that, alright, hell yeah. Home stretch. Got some more juice. We're still going to do an angle. Let's do an angle of 5. You know, well, I guess it doesn't matter. Angle of 10. So if we have an angle of 10, and then we're going to do this to it, we're going to take that angle of 10, add 90. That would be here, but we're going to double it. You know what I mean? So we're going to actually go to 180. You know what I mean? So you do you on, you know, do I want to go 10 plus 90, which is this, because this is 10, this is 10, and then this is, yeah, 10 plus 90. Cool. Or, and then multiply by 2, which is going to take this angle, and oh, it's actually going to come out here. You know what I mean? It would actually go out 20. This would be 10, and this would be 10. So it's probably better to do. So this is 2 theta. It's probably better to be like, hey, theta. Theta is going to be 10. Cool. So 2 times 10. My initial angle is 20. And then if it's theta plus 90, it's going to be 10 plus 90, and then double it. And we just showed that that's going to be 20. I don't know. Yeah. So, yeah, you just have to do whatever you need to do. But, so this is comparing the difference between cosine 2 theta and 2 times theta plus 180, because that's going to be cosine 2 theta plus 90. Doesn't seem like that, but hell yeah. When we go theta plus 90, that's going to be 2 theta plus 180, and that comes out of left field. So To begin with, we had 2 theta, that was going to be 20, and now we have 2 theta plus 180. At least that's visually easier, and now we can begin. So if I have 2 theta, this is going to be the sine component of 2 theta, and this is going to be the cosine component. When I have cosine 2 theta plus 180, or cosine 2 theta plus 90, however you're going to think of that. This is what I'm going to get. This angle right here. Vertical is my sine. Still vertical is my sine. It's just negative. It's the same. It's just negative. Alright, so horizontal is my cosine. So over here, if this is my hypotenuse, horizontal is my cosine. And so it's just negative. So now we can see that like cosine of 2 theta plus 90 is just going to be negative cosine theta. So theta plus 90 gives us that strain in that y prime direction, but we want it in terms of theta, not theta plus 90. If we do theta plus 90, we're just good to go. That's just going to be ex prime, where we go theta plus 90. But we want to throw in, we want to get a modified equation. We want to take ex, modify it, where we can just throw in theta and get ey prime. Sorry, we're going to take ex prime and modify it, where we can just throw in theta, and that's going to pop out ey prime. And all we have to do is take this equation and see this is cosine 2 theta. So anywhere we see a cosine, bumped it up. So this is going to be negative cosine 2 theta. I didn't even do this right. You know what I mean? This part's going to be the negative. If I have positive cosine 2 theta, this is positive cosine 2 theta. This is 2 theta. This is 2 theta plus 90. Okay, so this angle right there is 2 theta plus 180. And so, all right, let's do it right. So cosine 2 theta plus 90 is going to be equal to negative cosine 2 theta. Hell yeah. Sine 2 theta plus 90. Sine 2 theta plus 90 is going to be equal to negative sine 2 theta. Even here it looks like I should have put the negatives with these. And I mean, what we're saying is that sine 2 theta plus 90 is going to be negative. It's going to be a negative answer, but we can just tell by symmetry that it's going to be this is going to be the same as the cosine of 2 theta. It's just going to be negative. So hell yeah, this component, cosine of 2 theta plus 90, is just going to be cosine 2 theta, but negative. Hell yeah. Sine of 2 theta plus 90 is just going to be sine 2 theta, but a negative. So those are our two things that we will use. But check it out. If we do cosine, yeah, because we're going to have, oh, that's it. All we have is a cosine 2 theta and a sine 2 theta. Sweet. So what we get is for this cosine 2 theta, yeah, and so now we need to get the negatives to the other side. You know what I mean? Oh, never mind. Holy hell. So yeah, no, this plays, because I just didn't, right here as I'm showing, I'm throwing in theta plus 90 into that, and I'm throwing theta plus 90 into that. So this is going to be the y prime. If I do that, if I throw in theta plus 90, this is going to be ey prime. It's still going to be ex prime theta plus 90, but we're going to say that's ey prime. And I don't want it as theta plus 90, so I'm just going to use this identity. So cosine 2 theta plus 90 is just a negative 2 theta. You know what I mean? So I had a 2 theta, I'm just going to do this negative. So there you go. Over here, same thing. This sine theta plus sine 2 theta plus 90 is going to be negative 2 theta. Well, I had a 2 theta to begin with, so I'm just going to go negative. But hell yeah, so this term just becomes negative sine 2 theta. This term, after doing theta plus 90, just becomes negative cosine 2 theta. And then we got it. You know what I mean? So the positive one is going to be this positive cosine 2 theta, positive gamma divided by 2 sine 2 theta. That's EX prime. The EY prime is going to be this minus that cosine 2 theta minus gamma XY sine 2 theta. Hell yeah, so we did it. We rotated our element, and we found the new normal strains in this rotated X prime direction and the rotated Y prime. And so for another long video, we're going to go over, you know what I mean, how to get gamma X prime Y prime. We want, you know what I mean, if this is the plane stress, this thing's going to go that way, it's going to go that way, and it's going to shear in this direction. What we want to do is we want to take this element, rotate it up a certain angle, and then figure out how much it goes that way, how much it goes that way. No, for this, we want to rotate that element up and then see how much it skews, you know, to the side. This would be positive x1, y1. You know what I mean? That would be positive shear strain in the x prime, y prime. And that's what we do. And we're going to do that, you know, tomorrow or whatever. So hell yeah, we're done with this one. Booyah. That seemed brutal, but at least I don't think I actually stumbled a whole lot. I just kept repeating myself because this is no easy task, and I'm doing this for myself as well. But the first rodeo I couldn't figure out because they didn't do these boxes. You know what I mean? That for sure would have made this way simpler. And don't rotate this up and then change its length to a longer diagonal without showing. Yeah, that's tough. That's tough to but you don't have to do that. I was looking back at this and I was just like, well, check this out. So you can, if I said back to our page that strains this way and strains that way, and if I take this shape, cool, and let's say it strains by half, so it's going to become that shape. All right, now let's look at this one more time. Because if I take this shape and then just paint a diagonal on it, okay, and then when I strain it, it's going to go, you know, it's going to strain by 50%. And what's going to happen to this diagonal? That diagonal is going to be right there. You know what I mean? So, when we have this box, and this is our x, y prime direction, and we want to just say, hey, we're going to rotate it up an angle x prime, and then here's our new y prime. It's okay to be like, it's okay to associate because, well, what am I getting at here? No, I mean, this is interesting because this is what we're doing, but we're just saying, hey, this strain in this direction changes it a little bit, but hell yeah, this thing's also going to change in the y. That's going to bring this line up here. That's going to lengthen it that way, and then it's going to shear this way, you know what I mean, and that's going to lengthen this line over here, and then so all of those are additive. So we're going to have one of those and basically two of these, and so I don't know if yeah, I don't know. Like even this, I'm getting a little bit heady, where it's so much simpler to be like, hey, I just want to rotate this friggin' element, so rotate it, and then know that yeah, it's difficult to find the changes in length of a diagonal, so just box something in, you know what I mean? Which literally is this box. It's back to that box. So you're rotating it and then realizing it's just like, well, I really don't know what this is going to do. That's what I'm wanting to find out. And so I really only know what a box in this direction and this direction does. And so that's, but this line is going to lengthen. So but this was okay. You know what I mean? Just the fact that, hey, this shape is going to do this. It's going to lengthen in that direction and lengthen in that direction. And you can do those two separate things. And if we paint a line on it, that line is going to go, you know what I mean? And visibly, that line is going to change in length. And so if we go up here, that line is going to change in length. But we have to do the superposition. So I'll just end with just kind of a nice little superposition. We have this little shape. We're going to paint on that line. First, we're going to go strain in this direction. That line is going to be here. It's going to have a change in length of that. Draw our next one. Same shape, same diagonal. We're going to have strain it in that direction. It's going to go up here. And then so have hypotenuse, you know what I mean, do your right triangle. So this is going to be the change in length. And then the last one, because you're super positioning all these, this is your little element, and we're going to shear it at this angle, and it's going to rotate that angle. And so this line is going to go over here. Again, we want to know the change in length of this, so we're going to drop this down, have a nice little right triangle. This is my hypotenuse, and booyah. And basically all of these can be done by this angle theta. And that's going to be synonymous with, what we did was found the length of the diagonal, and that's the same thing as what we're doing here, is taking this element, rotating it up to here, knowing we need to find the change in length of this, but that's basically, we're going to treat this box as that diagonal, do this, it lengthens to there, do this, it lengthens to there, and then do this with it. And then it lengthens to there. And we're going to take the components in the direction of that lengthening. And that's going to be the change in length, the next one. Divide it by the initial length. That's why it's just so much easier if you have this initial length dx. But in the textbooks, they'll call this dx prime. You're going to have strain in the x, dx divided by dx prime, something cosine, plus strain in the y, probably dy, you know, something cosine, dx prime, and then strain in the gamma, dy, sine cosine, dx prime. And you just have to know that this is, you're picking up another cosine term, picking up a sine term, picking up a sine term. I think that's just one extra step. And so that's where this other term's a cosine. You get cosine squared, sine squared, and this other term's a cosine squared. And so, but hell yeah, I'm just enjoying rapid firing my way through here because it's very tedious, a lot of places for sign errors, and it just involves hella trigonometry. So hell yeah, so we're done with this. Thanks for joining me for tonight, and booyah.